For today is to talk to you guys about periodic trends. If you look in your packet, we are on pages 4, 5, and 6. So here's page 4, here's page 5. So these are mostly guided notes for you to take as you watch this video. And then page 6 is some practice problems for you guys to do. All right, let's get into it. So we're going to be learning about periodic trends. So goals for today. So you guys should be able to explain trends in reactivity based on number of valence electrons. So basically, how does the number of valence electrons change how things react? So like how many bonds it forms. And this is review. We've seen this before. And then two new things. You guys should be able to label your periodic table from increasing to decreasing values for the trends of electronegativity, atomic radius, and ionization energy. And you should be able to explain why the trends in electronegativity, atomic radius, and ionization energy occur. Obviously, you should also be able to define all of these words, which again we'll get into in a bit. So review. Go ahead and pause your video and think about this for a little bit. So you guys should get a proton and an electron will attract, right? So remember, electrons are attracted to our positive nucleus. And go ahead and pause your video and think about this one for a little bit. You should get that two electrons will repel, right? They both have negative charges. They will repel each other. Okay. So let's get into the new stuff. So electronegativity. So sort of the fancy definition, electronegativity is the relative ability of atoms to attract shared electrons. So basically what this means is electronegativity is how much atoms want electrons. So the more electronegative something is, the more it wants electrons and the more it pulls them towards it. So here's the trend in electronegativity. And I'm first just going to talk about this trend from left to right. So electronegativity increases as you go from left to right. And you can see if you look on this table, you can see this actually as the numbers for electronegativity, right? So for example, lithium is 1, beryllium is 1.5, boron's 2, carbon's 2.5. So you can see very clearly it's increasing from left to right. So the reason why that happens, so as you go from left to right on the periodic table, atoms want electrons more because these atoms over here, these nonmetals, remember nonmetals tend to gain electrons when they form bonds. So these guys are really the ones that want electrons. And let me go ahead and show you guys some Bohr diagrams to really cement this. So I've drawn the Bohr diagrams for lithium, which is right here, boron, which is right here, oxygen, which is right here, and fluorine, which is right here. So let's think about if each one of these were to form bonds, what would it do, right? So remember, our goal in general is that atoms want 8 valence electrons. But to be even more specific than that, really what they want is atoms want a full outer shell of electrons. Atoms want a full outer shell of valence electrons. Because this is what will make them the most stable, right? They're the most stable when they have a full outer shell of valence electrons. So fluorine, for example, let's look at this. Fluorine is missing 1 electron here, right? It's got 1 spot where it could add 1 more. So fluorine really wants to gain 1 electron. Oxygen, we can see there's a spot for an electron here and a spot for an electron here, right? So oxygen really wants to gain 2 electrons. Gain 2 electrons. Boron. So here's the thing about boron. It kind of wants to lose electrons because if it loses this electron, it loses this one, and it loses this one, well, then there's nothing in this outermost shell. So we'll go to the next shell in, and this shell right here is full, right? So it's going to be easiest for boron to lose 3. The other option, if it tried to gain, is it could try and gain and get to 8. So it would have to gain like what, 1, 2, 3, 4, 5 electrons. Boron doesn't want to gain 5 electrons. It would rather lose 3. So boron wants to lose 3. And lithium right here. So we could try and give it some more electrons. We could go 1, 2, 3, 4, 5, 6, 7. We could try and give it 7 more, but it really doesn't want to do that. So what it wants to do is it wants to lose this 1 electron. So the next shell in this shell here becomes the outer shell, which is full. So it wants to lose 1. Okay, so let's think about how this applies to electronegativity. So electronegativity is how much atoms want electrons, like how much they want to attract electrons towards them and to get more electrons, right? Well, fluorine and oxygen both want to gain electrons, so they're going to have high electronegativities. Lithium and boron don't want to gain electrons at all. They want to lose electrons. They want to get rid of some of the electrons they already have. So they're going to have low electronegativities, right? So we can say sort of on the left side of the periodic table, you'll have a low electronegativity. And then as you move towards the right side, we will get to atoms that have more of a high electronegativity. So that's sort of why that trend there happens, right? As you go from left to right, you get atoms which are closer and closer to having a full octet. And so then they really want to just gain that extra electron. And so they have a high electronegativity because they want to gain an electron. I want to talk about the noble gases for a second, right? So these guys right here are the noble gases. And if we go back to our nice little chart with all of the electronegativities, you will notice they are missing. There are no noble gases on here. So we kind of don't really think about the noble gases as even having electronegativities, or if they did, they would be really low, because the noble gases already have full octets, right? They have full outer shells. So the noble gases really do not want to gain electrons. They don't want to lose electrons. They don't want to react at all, right? So when I say from left to right, the electronegativity increases, ignore the noble gases, right? Even though the noble gases are at the end over here, they do not have the highest electronegativities because they have like pretty much none. They do not want electrons. I want you guys to pause for a second and think, which atom on the periodic table has the highest electronegativity? So pause the video for a second and think, which atom has the highest electronegativity? So it is fluorine, right? Because as we go from left to right, it increases, and then as we go down, it decreases, right? So fluorine has the highest one. And if you were to look at the numbers, you'll see fluorine has an electronegativity of 4, which is the highest number. Which brings me to a bad pickup line. If I were an electron, oops. If I were an electron, you'd be fluorine because fluorine is the most attractive element on the periodic table. So fluorine is the most electronegative element on the periodic table, so it attracts electrons the most strongly. Pickup line probably doesn't work, but if it helps you to remember how electronegativity works and it helps you to remember that fluorine's the most electronegative, I'll take it. Okay, right, so this, again, electronegativity increases from left to right, decreases going down. There's just another picture of it. And then why does this happen? So I talked a little bit about why it increases from left to right, right? Because atoms get closer to having a full shell of 8 valence electrons. So they really, really want just a few more electrons to fill in that shell. So when we look at, for example, like oxygen and fluorine, fluorine has a higher electronegativity than oxygen because it's really, really pulling on that last electron. Like it just needs one more. Whereas oxygen has still got a pretty high electronegativity, but it wants 2 more electrons, so it's not quite as strong. And then let's talk about as you go down the periodic table. Why does electronegativity decrease? So it decreases as you go down the periodic table because there are more shells of electrons, which block the pull of the positive nucleus on the negative electrons. And this is called electron shielding. So let me go ahead and explain electron shielding a little bit. So let's see. So the electrons in the inner shells shield the outer electrons from the pull of the positive nucleus. And let me go ahead and draw a picture because I believe that will help. So this is electron shielding. Let's see. Let's draw sodium. Everyone loves sodium. Let's see. How many electrons has sodium got? Sodium has 11 total. Okay, so I need to draw 11 electrons in my picture. So my first shell can hold 2. That's full, so I go to my second shell. So that can hold 1, 2, 3, 4, 5, 6, 7, 8. And then my third shell holds 1. And you know what? Let's go ahead and compare that to something that's similar to sodium. Let's see. So if I look at this, here's sodium, here's lithium. They're in the same column, so I'll draw lithium. And lithium only has 3 electrons. So here's lithium. Here's its first 2 electrons that fill up the first shell. And here's its next electron. Okay. So electron shielding is the electrons in the inner shells shield the outer electrons from the pull of the positive nucleus, right? So remember, the nucleus has a positive charge, right? It is full of protons, which are positive, and neutrons, which are neutral. But right now we really care about the protons, right? And these electrons are negative, right? So they are attracted to this positive nucleus. But let's go ahead and compare this electron here, lithium's valence electron, and this electron here, sodium's valence electron. So lithium's valence electron has a couple of electrons in the way, but not too many. So it's got a pretty strong pull towards the nucleus, right? Again, that negative charge is being attracted to that positive charge of the nucleus. Well, sodium's electron, I mean, it's negative. It's attracted to the positive nucleus, but it's got all of this stuff in the way. It's got all of these negative electrons in the way, right? And remember, we know that negative and negative charges repel, right? So this electron is attracted towards the positive nucleus, but it's also repelled by all of these negative electrons that are between it and the nucleus. So what this means is this electron here of lithium is going to have a much stronger pull towards the nucleus than this electron in sodium. And so there's a couple of things that this means for like the properties of atoms. So for one thing, it is harder to get rid of lithium's electron, right? Because it's really strongly attracted towards this nucleus. So it's going to take more energy to get rid of it. And then if we think as far as electronegativity, right? So remember, electronegativity is how much atoms want electrons, right? High electronegativity, I really want more electrons. Sodium and lithium might not be the best example for this because they don't particularly want more electrons. But sodium is going to have the lower electronegativity. Because again, they don't particularly, these guys in particular don't want electrons, but sodium would want them even less than lithium because not only does they both have one valence electron, but sodium's got all of this negative charge, right? So it's really not pulling in those electrons that strongly. So it's going to sort of want electrons less because of all of this electron shielding, all of this negative charge here. Okay, so that's electron shielding. And let's go back here, right? So the more electrons you have in the inner shells, the less strong the pull of the nucleus on the valence electrons is, right? Because you have all of that negative charge and it's sort of blocking the positive charge of the nucleus from pulling in electrons. And so the easier it is to lose valence electrons, the more electrons you have in the inner shell. Okay, ionization energy. So we've briefly talked about ionization energy before. So ionization energy is the energy it takes to remove a valence electron, right? So you guys remember we talked about how you need to add energy in order to remove a valence electron, right? Because that electron is negative, it's attracted to the positive nucleus, and if you want to rip it away, you've got to add energy in order to do that. It doesn't really want to leave that positive nucleus. So first ionization energy is exactly what it sounds like. It's just the energy to remove the first valence electron. And so when I talk about trends in ionization energy, I'm talking about the first ionization energy. Because to keep it simple, we're just going to compare how much energy it takes to remove the first valence electron from an atom. It would be hard to draw a nice little graph with the periodic table and compare like every single electron in every single atom. So when I talk about trends in ionization energy, I'm really talking about the trend in first ionization energy. So like, for example, compare between oxygen or fluorine, like which one does it take more energy to remove the first electron from? That would be like talking about first ionization energy. Okay, so we know in general, I go back to this, right? Atoms on the right side of the periodic table, so nonmetals, they want to gain electrons, and these guys want to lose electrons, right? So you can see right away, since these guys want to lose electrons anyways, they're going to have lower ionization energies. Lower ionization energy, right? Like you're still going to take some energy to get rid of that electron. It's still attracted to the positive nucleus, but it's not going to take quite as much because they kind of want to lose it in order to become more stable, right? And then these guys over here are going to have higher ionization energies because they don't want to lose electrons at all. They want to get even more electrons, right? So they will have a higher ionization energy. So let's go ahead and go to the PowerPoint slide on that. Here we go. Right, so we can see that ionization energy increases as we go from left to right. Again, the ones over here, the metals have less valence electrons. They actually want to get rid of them, so it's not going to take a ton of energy to get rid of those electrons. And then these atoms over here have more valence electrons, and they want to get even more electrons to get that full outer shell of 8. So it's going to be a higher amount of energy to remove those. Okay, so let's think about as we go down. So again, as we go down, we need to think about electron shielding. In general, whenever you think about a trend that goes down on the periodic table, or just like the sort of the up down, the vertical direction, think about electron shielding, because that's mainly what's different between all of these atoms in a column, right? Is they just keep getting more and more shells of electrons. So let's see, let's go ahead and go back to our pictures. See if I can maybe erase some of the things I've circled on here. Actually, you know what? No, I'm just gonna redraw them. We'll just draw sodium and lithium. Right. So remember, on a periodic table, lithium's up here. Actually, you know what? We can even let's draw. We'll do hydrogen, lithium, and sodium. We'll get like little bit of this column here, right? So here's hydrogen. We got 1 valence electron. Cool, cool. Here's lithium. We got 3 total, 2 in the inner, 1 outer. Here is sodium. We have 2, and then 8. And then 1, right? Okay, so as we go down, ionization energy decreases. If I draw a line there as we go down, ionization energy decreases as you go down a column. So let's think about that. So when I say ionization energy decreases, what I'm saying is it takes less energy to remove an electron, right? Let's go ahead and write that. So AKA it takes less energy to remove an electron. So why would it be easier to get rid of this electron than this one or this one? Well, it's electron shielding, right? So sorry. Here we go. Okay, so electron shielding. So this electron is attracted to this positive nucleus, but it's got all of these negative electrons in the way, right? So it's not super attracted. We can get rid of it without too much trouble. This electron here is attracted even more strongly to the positive nucleus because there's less electrons in the way. And this electron here is attracted really strongly to the positive nucleus because there's literally nothing in the way. It's just an electron and a proton, right? So that's got a really strong attraction, right? So the stronger the attraction of the electron to the nucleus, the more energy it's going to take to tear that electron away, right? So as we go down a column, as we go from hydrogen to lithium to sodium, it takes less and less energy to remove electrons because we keep getting all of these negative charges in the way that are blocking the electrons from the nucleus, right? So it becomes easier to remove electrons as we go down a column. So ionization energy, which is the amount of energy it takes to remove electrons, decreases as you go down a column. Okay, so that's ionization energy. Let's talk about atomic size. So atomic size is pretty much what it sounds like. If you want a vague definition, you could say it's how big an atom is. But more specifically, it's really about how far the valence electrons are from a nucleus, right? Because if you think about what an atom looks like, the nucleus is pretty small, and most of an atom is like a bunch of electrons and kind of like the empty space where those electrons are, right? Like you've got this tiny electron, and then you've got all this like huge empty space that's just kind of wandering around in near the atom. So let's talk about atomic size as we go down a column or down a period, because that's sort of the easier one to grasp. And then we'll talk about it after that. We'll talk about it as you go across a row, because that one's a little bit trickier. So okay, as you go down a column, the atomic radius increases because you're increasing the number of energy levels. Like you're just flat out increasing the amount of electrons and the number of shells of electrons, right? So they show here like lithium, sodium, potassium. Let me go back to my picture here, right? If we think of like hydrogen, lithium, sodium, right? You can clearly see they're getting bigger because you just have more electrons. And not only do you have more electrons, but you have more shells of electrons. Like when you add a whole new shell of electron, that makes it's much bigger, right? So that's why we increase in size as we go down, because we're just adding more and more shells of electrons, and we're just building and building out. Okay, so that's why atomic size increases as you go down. So let's talk about atomic size as we go from left to right, because this is weird. So you might think as you go from left to right, atomic size would increase, right? Because, well, they're getting more things, aren't they? Right? Like lithium's got 3 protons, beryllium's got 4, boron has 5, and so on. So we're getting more protons and more electrons as you go from left to right. So you might think, well, there's more stuff, so it's bigger, right? But here's where the idea of the atom is mostly based on the electrons and how much space they take up. Here's where this comes in. So the atomic radius actually decreases as you go from left to right. Right, so atomic radius decreases as you go from left to right. So what happens is you get more and more protons as you go from left to right, right? So more and more positive charge. And the more positive charge you have, the more that pulls in on the electrons. So you're actually decreasing in size. Let me go ahead and draw a nice picture for this. We'll go, I don't know, boron, carbon, and nitrogen or something like that. Right? So let's see if I can, there we go. So boron has 5 protons, so it has 5 electrons. Carbon has 6 protons and 6 electrons. Nitrogen has 7 protons, 7 electrons. Right, so I'll go ahead and draw these 5 pluses, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So here's boron. Let's see, let me erase that so I have enough room. Right, so let's see, boron's going to have 2 electrons, and then it's going to have 3 electrons. And the 5 positive charges will pull on the electrons a little bit. Carbon has 6 protons, right? So it's got more protons. So what's going to happen is those 6 protons will pull on the electrons even more. So the electrons will get just a little bit closer in. And then nitrogen has 7 electrons, so they'll get even closer, right? So 1, 2, 3, 4, 5, 6, 7. Should probably draw that a little bit smaller for emphasis. 3, 4, 5, 6, 7, right? So atomic size decreases as we go from left to right across a row, right? Because you're getting more protons, and those protons are pulling in the electrons. And you'll notice I didn't increase the number of shells of electrons, right? Like boron has 2 shells, carbon has 2 shells, nitrogen has 2 shells, right? So because I'm not increasing the number of shells of electrons, I'm able to just kind of take the few extra electrons that I'm getting and just kind of pull them in a little bit more because I'm getting more protons. So basically, as you go from left to right, we really, really care about the number of protons. Like that's what's affecting the size, right? So more protons equals pull in electrons equals atom size is smaller. Okay. And that is pretty much it. So I just want to do a couple of these examples with you guys. So if you look at the homework, you've got the guided notes, which you should have just filled out. And then there's a couple of practice questions, basically where I gave you guys a couple of different elements and I asked you to compare some things. And so once you have your periodic trends written down, these are pretty easy to do. So let's go ahead and do this one, for example. So select the element in each pair with the larger atomic radius. So I'm comparing Li and K. So let's see, let me draw my atomic radius trends. There we go. Okay. So we just talked about how atomic radius increases as you go down, and it decreases as you go from left to right. And if it helps, you can also draw the reverse, right? So for example, if atomic radius increases as you go down, it must decrease as you go up. And if atomic radius decreases as you go from left to right, then it must increase as you go backwards. Okay, so they asked us to compare lithium and potassium. Here's lithium, here's potassium. And so I know my trend as I go down is that atomic radius increases, right? So that tells me that lithium must be smaller and potassium must be bigger. So if I were to compare them, I would say that the radius of potassium is greater than the radius of lithium. And so you guys can do the same trick if you're given, for example, ionization energy or electronegativity. You just have to draw the trends, right? Okay, so that is it for today, and I will see you guys later. So bye.